So as Samir was saying, I want to discuss some questions of polymer optimization, and namely how to analyze the convergence of some approximation hierarchies. So this is based on some joint works with Etienne de Klerk from Tilburg and Lucas Slot, who is doing his PhD with me at CWI. Okay, so I think maybe not everybody is completely familiar with polymer optimization. So, and I got the advice that the talk should be accessible also for doctoral students. So I have some parts are a bit basic recaps. I hope it's fine. So what is polymer optimization? So we have a polynomial f, which we want to optimize, to minimize, I will take in this talk, about over a set K, so visibility region, which we will assume to be compact, and in most cases, but sometimes we may not need to assume it, semi-algebraic, which simply means that K is defined as a solution set of a system of polynomial inequalities. So the object we want to understand is the minimum of f, which we call f min. So the minimum value that f takes over a compact set K. So, and here I just saw an example. This is a Motzkin polynomial, to which we will come back later, which we want to minimize over the box. So this is a very general problem which falls within nonlinear optimization because we have polynomials. So it's very general, and nonlinear optimization is of course a very wide field. And even if you restrict yourself to polynomial, you still have a very wide class of problems which captures all kinds of instances in control, in combinatorial optimization. And this contains all kinds of NP-hard problems. So I just decided to just name one combinatorial optimization problem, which can be reformulated using this framework of polynomial optimization. So if you have a graph G, you want to find the maximum cardinality of a stable set, and this number is called alpha G, that's a stability number. And this is a very, this problem is very basic, it's NP-hard, and you can reformulate it as several instances of polynomial optimization. You may decide to optimize a polynomial of degree 2 over the hypercube over the simplex, or to optimize a polynomial of degree 3 over the sphere. So, and here are these reformulations. So on here we have an expression of alpha as maximizing this very simple quadratic polynomial over the cube. And here 1 over alpha, you get it by minimizing this quadratic form on the standard simplex. This is Motzkin-Strauss reformulation. And here is yet another reformulation due to Nesterov, which tells how to compute alpha via this formula as maximizing a polynomial of degree 3 over the unit sphere. So from this, we see that as soon as you have nonlinearity, so here's the objective function as degree 2 or 3, optimizing over very simple regions like the cube, the simplex, or the sphere, these are already capturing NP-hard problems. So these are hard problems, but yet what one can do is to try to derive some hierarchies of bounds which converge asymptotically to the minimum of f. So what I will, and for this, as we will see, we are going to exploit heavily the algebraic structure which is present in polynomials. And by exploiting this algebraic structure, we are going to be able to get to the minimum, to the global minimum, while usually in nonlinear optimization, one can get to local optima only. So what I will do in this talk, first I will do a short recap on the hierarchy of lower bounds based on sums of squares, which is probably what most of you are most familiar with. And then I will move on to a hierarchy of upper bounds for the minimum, which is so-called measure-based. And the rest of the talk will be to try to give some information on the convergence analysis of the bounds. So let me start with a brief recap on the most usually studied hierarchy of lower bounds for polynomial minimization. So here is the problem we're interested in. We want to minimize f over k. So very quite obviously, this is the same thing as trying to find the largest scalar lambda for which the polynomial f minus lambda is non-negative over the set k. Yeah? And now, if we assume that our set K is semi-algebraic, which means that it is a solution set of a bunch of polynomial inequalities, G1x non-negative, Gmx non-negative, then there is something we can do in order to attack this problem. And namely, we replace this condition, this non-negativity condition, saying that f minus lambda non-negative over K, which is hard. We replace it by an easier condition. And this easier condition is saying that we try to write f minus lambda as a weighted sum of sums of squares, so such a decomposition, where the weights are the constraints defining the set K. So we are now searching for the largest lambda, scalar lambda, for which f minus lambda admits such a decomposition S0 plus S1G1 plus SMGM, where the Sj are the unknown, which are sums of squares of polynomials. And we put ourselves a degree bound on the degree of these unknown sums of squares. So we pick some integer r, which will be our target degree, and we restrict ourselves to sum of squares polynomials for which each summoned Sj, Gj has degree at most 2r. So, and in this way, we obtain a parameter fr, which is the usual Lasserre lower bound for polynomial optimization. So for every such degree r, we get the parameter fr, which is a lower bound for the minimum. If we let the degree r grow, we get a bound which is better and better, so it gets closer to the minimum. And the nice property is that these bounds converge asymptotically to the minimum of f over the set K, when you let the degree r tend to infinity. Yeah? So this result holds under a condition on K. It should be compact. So throughout the talk, the set K will be compact. And plus one small additional condition, which is a so-called Archimedean condition, which, for instance, you may just think that, okay, the set K is compact, so it contains a ball, and let's just take the equation of a ball which encloses the set K, and we put it explicitly in the description of the set K. So it's a very minor condition, which essentially the set K is compact. So this convergence result of Lasserre is relying on the so-called positive Stellensatz by Püttiner, who showed that if you have a polynomial P which is strictly positive on K, then it admits such a decomposition. So if P is strictly positive on K, you can find multipliers Sj so that P admits such a decomposition. And now from this, it's very, it's not difficult to see that, to show the convergence of this lower bound to the minimum of f. And why are these bounds interesting? Well, they converge to the minimum, which is nice. But the second nice thing is that if you fix the degree r, then the bound fr, the parameter fr, can be computed efficiently using semi-definite programming. So here the workhorse I am referring to is the fact that checking whether a polynomial is a sum of squares can be done with semi-definite programming. So all this unknown S0 up to Sm, we can deal with them, we can find them using semi-definite programming. So I suppose that most of you know this, but yet I have inserted one such slide in order for the people who maybe are less familiar with this fact, because this is really the working horse of the whole theory. Yeah. So the claim once more is that one can test sums of squares of polynomial using semi-definite programming. And here is, in a few lines, why is this true? So here is our polynomial f, which we want to check whether it's a sum of squares or not. Well, first of all, it better be of the even degree, otherwise it's not going to be a sum of squares. So we take f, which has even degree 2d, and we try to write it as a sum of squares of polynomial pi. And pi is going to have degree at most d. So we can write it as the inner product between its vector of coefficients. This is what I mean with pi bar. So the inner product between the vector of coefficient and the vector of monomials up to degree d. So here x to the alpha is the monomial x1 to the alpha 1, x2 to the alpha 2 up to xn to the alpha n. And I stack the monomials and I make a vector out of it. And then the next step, you just unfold this square by putting first, so here I've written each pix in the same way, but interchanging the two factors in the scalar product. And the next thing is just bring the summation inside. And now we see that this sum of pi transpose, this is, if you call it M, this is a typical positive semi-definite matrix. So what did we learn? We learned that F is the sum of square of polynomial if and only if I can find a matrix M, which is positive semi-definite, and which satisfies this identity. So we have an identity, f of x is equal to the monomial vector x alpha times m times x alpha. So we have a polynomial identity, and now it suffices to equate the coefficients on both sides of this identity. So f alpha is equal to the coefficient of x alpha here, and this is exactly what you get, what is expressed here. So in summary, F is the sum of squares of polynomial if and only if there exists a matrix M, positive semi-definite, which satisfies this system of affine equation. And this is typically an instance of semi-definite programming. So this is known as the Gram matrix method by Powers and Verman. So this is a workhorse of the whole thing. We can check whether polynomials are sums of squares efficiently using semi-definite programming. While testing whether a polynomial is non-negative, we don't know how to do this. This is a hard problem. So here is a small example. So the slides will be posted, so you can check the example slowly. So I've just recalled what are this, how is this hierarchy of lower bounds built for finding the minimum. So we have bounds, they converge to the minimum of F. And then the next natural questions would be to understand how fast FR tends to the minimum. So can we bound the difference F min minus bound in terms of R? And there is a result by Nie and Schweighofer which gives such a result. So here is the dependence on R. So you see you have the dependence on R is logarithmic, is log R. And there is also this square root with the base C, where this parameter C is a constant which depends on the compact set. So it's nice because it shows again the asymptotic convergence, but the convergence is rather slow. So I was just showing you this result of Nie and Schweighofer, which gives a very general convergence analysis for this hierarchy of lower bounds. But the dependence on R is a bit disappointing. Logarithmic, and there is this dependence, this unknown parameter C, which depends on the compact set. So naturally, the question is, can we do better? Can we do a better convergence analysis? This is actually quite tricky, and there is some research going on very recently. And I want to mention this very recent result by Fang and Fuzzy, who give an improved convergence analysis for the case of the unit sphere. When K is a unit sphere, then actually you can show a convergence analysis in 1 over R square, so quadratic. So it's much nicer. So, and this is the best you can do because this is also tight. The analysis is tight. So, but that's about the state of affairs about the convergence analysis for the lower bound. But once again, people, it's an active research area in the moment. But now what I want to move on is so I have discussed so far the lower bounds, and now I want to discuss the upper bounds. So we start again. I will now describe how to build a hierarchy of upper bounds for the minimum of F. So we start again with the expression of the minimum. So you want to find a point X in K, which minimizes F of X. And now the very basic observation is that you are going to identify points with Dirac measures. And if you think in this way, then it's very easy to see that to find the minimum of f, this is equivalent to asking yourself, find the probability measure nu on k, for which the expected value of f with respect to this probability measure is minimum. And to see this equality, just replace x by the Dirac measure. And so this is a very easy observation. But the first result due to Lasserre is that actually in this optimization problem, we don't need to optimize over all probability measures on k. What we can do is fix one measure mu on k, and then you look at all the measures nu which have a density function with respect to this fixed measure mu. So that's the first thing. And then the next thing is actually you don't need to look at all continuous density function. It's enough to restrict yourself to sum of squares density function. So this is a claim. The minimum of f, you get it by searching for a sum of square h, which gives you a probability measure on k. So, and this means that integral of h d mu is equal to 1. And then you minimize the expected value of f with respect to this measure. So the measure where you have this density function h with respect to mu. So this is quite intuitively rather clear in a sense, because what you do is you have the Dirac at the global, you pick a global minimizer, you look at the Dirac at the global minimizer, and now you try to approximate this by a continuous function, which of course you can do, and continuous function you can approximate by polynomials and by sums of squares. So intuitively, it's rather clear that why this should be true. So if we want to get bound, so now what we do is you take these density functions h, and you restrict yourself to density functions of a given degree 2r. And in this way, you get a bound, fr, which is just the same definition, but you restrict yourself to searching for density function, which are sums of squares of degree at most 2r. So in this way, we get upper bounds for the minimum, and they converge to the minimum of f. And each bound, if you fix r, you can compute it using semi-definite programming, because this involves the sum of square. But it's a rather simple semi-definite program, and because it has only one equation, and as we will see a little later in the lecture, actually it's just an eigenvalue problem. It boils down to an eigenvalue problem. So it is way simple. But there is a but, which is that in order to compute all these things, you need to know the moments of the fixed measure you have considered. So the moments are just the integral of x alpha d mu. Because if we look at what is the integral of f d mu for a polynomial, then you see that if you express f in the monomial base, then you can express it linearly in terms of the moments. So if you want to compute this bound, you need to know the moments. So that's a restriction, of course, but these moments are known when you look at simple sets like the cube, the ball, the simplex, and simple measures like Lebesgue or other measures, or like the Haar measure on the sphere. And as we observed in the very beginning, such simple sets already carry some NP-Haar problems. So already for such simple sets, it's interesting to be able to understand how these bounds behave. So here is a simple example. We go back to the Motzkin polynomial, which we want to minimize over the box. There are 4 global minimizers. And here are the density functions that you get if you would compute these bounds as the optimal density function of degree 12, of degree 16. So we see that the optimal density function is behaving like approximating a convex combination of Diracs at the 4 global minimizers. And as expected, when the degree grows, the peak, so the sum of squares become more peaky at the 4 global minimizers. So this is the topic of this talk, is actually to try to understand what can we say about the rate of convergence of this upper bound to the minimum. So this is what I call ER of F. It's the range between the upper bound FR and the minimum of F. So it depends actually on the measure you fix yourself on the set K, and it depends on the set K, of course, but we don't put this notation in order to simplify the notation, but you should keep in mind that this parameter will depend on the measure we fix. So in this table, I show you what we can do, what are the results which we know. So the first case to do is a case of the hypercube, and the most simple is to do just the one-dimensional hypercube, so an interval -1, 1. And as we will see, this is actually the basis case from which we are going to be able to derive lots of other following results. And so for the hypercube, or for the interval -1, 1, we take as fixed measure a measure with such a weight with respect to the Lebesgue measure. So 1 minus x squared to some lambda, where lambda bigger than -1, this is the Jacobi weight. And if you would take lambda is -1/2, this is a Chebyshev weight. So I distinguish because, as we will see, for general Jacobi weights, we will be first able to do only linear polynomials, and for Chebyshev weight, we can do arbitrary polynomials. Building on these results, and we can deal actually with any Jacobi weight where lambda is at least -1/2 and any polynomial. And building again on these results, actually we can then deal with the case when this compact set K is a sphere, the unit sphere equipped with the Haar measure. We can deal with a ball equipped with such a weight measure. We can deal with other compact sets like the simplex, or what we call round convex body equipped with a Lebesgue measure. And in all these cases, we see that we can show the same convergence rate in 1/r², so quadratic in R. And finally, you may wonder, what about general convex bodies? So for general convex bodies equipped with a Lebesgue measure, then actually we can show almost 1/r², but we have this logarithmic factor, log r². So it's probably not the best answer, but it's almost the best answer. And for the red results, so 1/r², we are going to use two different techniques actually to show these two groups of results. So what I want now to do in the rest of the lecture is to give some ideas on how to show this convergence analysis. So there are two key strategies which we are going to use in the proof. So the first strategy which will be based on reformulating the parameter as an eigenvalue problem and relating it to roots of orthogonal polynomials. Building on that and using additional small tricks, we are going to be able to transport the result 1/r, means the convergence rate in 1/r², which we could show for the univariate case. We can transport it to more sets and more measures. So that's the first key technique: reformulate as an eigenvalue problem and relate to roots of orthogonal polynomials. And the second key technique will be to go back to the starting point that we were trying to build a nice sum of square densities, which looks like the Dirac delta here, combined with push-up measures. And this will deliver us the almost optimal, suboptimal convergence rate for general convex bodies, K. But there again, the idea will be to reduce in some way to the univariate case. So the univariate case, as can be seen from this slide, the univariate case is actually quite crucial to understand in the whole story. Okay, so there are a number of basic tricks which we will need to use in order to make our life easier in order to deal with this. And let me mention a first very simple basic trick, which essentially tells that it's enough to worry about quadratic and separable polynomials. It's a very simple trick, which is based on Taylor's theorem, but it's a very, very useful trick. So we have our polynomial f, which we want to minimize over k, and let a be the global minimizer. And let's call gamma the maximum norm of the Hessian of f over the set k, so it's a constant. By Taylor's theorem, f, you can upper bound it by this quadratic function here, which I'm showing here. Let's call it g, this polynomial. So it's so this g has several properties. It is quadratic, and it is separable in the various variables. And the third important property is that g takes, if you look at the minimum of g over the set k, it's again attained at the point A, and it has the same minimum as f. So f min is equal to g min. So this is a very simple observation, but which permits us to conclude that the error of f, so this is a range between the bound fr and the minimum of f. So this range for f is upper bounded by the range for g. So if we can understand the behavior of the range for g, then we understand the error for f. And so this makes our life much easier, because this is telling us that it suffices to analyze quadratic polynomials. And sometimes it will even suffice to analyze linear upper estimator. We will see that this is the case, for instance, for the unit sphere. So this is the first basic trick. It's enough to analyze quadratic polynomials in a nutshell. Okay, so I want now to explain how we are going to analyze the bounds for the univariate case and for the very simple case when k is just the interval, because as I mentioned, this is crucial for the rest. And key to that is, let's start with giving an eigenvalue reformulation for the bounds. So this is the definition of the bounds again. So this eigenvalue reformulation is true in general for any k multivariate. So the key is, let's pick an orthonormal basis of the space of polynomials, orthonormal with respect to the basis measure we have fixed ourselves. This is this fixed measure mu that we take on the set k. Yeah? And let's define this matrix whose entries are what's given here, the integral of f p alpha p beta. So the first simple observation is that if you have a polynomial h, it's a sum of squares if and only if you can write it in this way. So this is a gram matrix method which I recalled at the very beginning of the lecture. At the beginning of the lecture, I was expressing my polynomial in the monomial base, but of course you can just pick any other base to apply the method. And here we do pick the orthonormal basis instead of the monomial base. And if we do this, then we see that we can reformulate the integral of fh as the trace inner product between this matrix M of f, which is a moment, if you wish, this is a moment matrix of degree r. So the trace inner product between this matrix MR of f with this unknown matrix x. And the integral of h d mu is exactly the trace of x. So this is very simple to see. And then using this, we see that the bound can be reformulated as this very simple semi-definite program. You want to minimize this objective function, and the condition on x are that the x should be PSD and the trace is equal to 1. So in other words, the bound is equal to the smallest eigenvalue of this moment matrix MR of f. I should say this was already in the original paper of by Jean Lasserre, this eigenvalue reformulation. So we see that this is again telling us that actually this bound is rather simple to compute. You don't even need to do semi-definite programming. It's just computing an eigenvalue of this moment matrix F. So the first result I want to explain is that for the univariate case, when k is interval -1, 1, one can analyze the bounds fr for the Chebyshev measure for any polynomial and for any Jacobi measure when f is linear. So as we have just seen in the first trick, it's enough to analyze quadratic polynomials. So I will do it in 2 steps. First, I restrict myself to f is linear. So linear in one variable, that's just f of x is x. And then we will do f is quadratic. So we are in the setting where k is the interval -1, 1, and f is linear, f of x is x. So it's not that it is such a very interesting case. In a sense, you may wonder, why do we care to minimize x over the interval -1, 1? This is not a very fascinating optimization problem, of course. But the point is that this analysis will be used to learn more results for more complicated situations. So this is the point of doing this. So, and here the analysis relies actually, so I have just explained that this bound is just the smallest eigenvalue of this moment matrix. And the point is that the smallest eigenvalue of this moment matrix is very well understood by going back to the classical theory of orthogonal polynomials. So we have this orthonormal base of polynomial with respect to our base measure, which we, and the point is that, I mean, the well-known fact is that the polynomials, orthogonal polynomials, satisfy a 3-term recurrence. And the next consequence of this is that this moment matrix for the polynomial f of x is x, which is defined here, it's actually a very simple structure. It's tridiagonal, and its eigenvalues are the roots of the next orthogonal polynomial, PR plus 1. So this is MR of x, and its eigenvalues are the roots of the orthogonal polynomial of degree R plus 1. So here is how the moment matrix looks like. This is really the basic theory of orthogonal polynomial. It's actually not difficult to check this. But if we put things together, then we can obtain that if you pick, for instance, the Jacobi measure, f of x is x, then the bound fr is, which is the smallest eigenvalue of the moment matrix, is equal to the smallest root of the orthogonal polynomial of degree R plus 1. And the point is that the roots of these orthogonal Jacobi polynomials are very well understood. So in particular, it is well known that the smallest root is -1 plus, it behaves exactly the 1 over R squared at the rate 1 over R squared. So from this, we deduce immediately what we wanted. So the bound FR is the minimum of F plus the rate of convergence is exactly 1 over R squared. So it's upper bound 1 over R squared, but it's also, it's tight. The analysis is tight. Okay, so this is dealing with the case when f of x is x. Let's go to f of x is quadratic of the form, say, x squared plus kx. 2 cases. Either the minimizer is on the boundary of our interval, and then it's easy again because we can find a linear upper estimator for f. So the error of f is upper bounded by the error of g, and we have just learned that in the linear case, the error behaves like a 1 over R squared, so we are done. And this analysis actually holds for any Jacobi measure, not only for the Chebyshev measure. Second case, the minimizer is in the interior of the interval, -1, 1. So let's just go back to what we just learned, that the bound is the minimum eigenvalue of the moment matrix. Now the moment matrix, which I show here, is going to be 5 diagonal, and it's almost tuplets. So for any Jacobi measure, it would be 5 diagonal. But now, since I am restricting myself to the case of the Chebyshev measure, we can see that it's almost tuplets. So it's tuplets except for the first two rows and columns where you have other more complicated values. And we have to understand what is the smallest eigenvalue of this matrix. And the trick to do this is to rely on the fact that we have these big 5 diagonal tuplets submatrix sitting in it. We don't like the first two rows and columns because they have a bit complicated entries. Well, what we are going to do is replace the first two rows and columns by the numbers you need in order to make a circulant matrix C. So you adaptively change the entries in the first two rows and columns to embed B in a symmetric circulant matrix C of size R+1. If we do this, then we know that the smallest eigenvalue of our original matrix is at most the smallest eigenvalue of B, which is in turn at most the third smallest eigenvalue of C. But C is circulant, so we can compute its eigenvalues and we can precisely understand how they behave, and this concludes the proof. So using this argument, we can obtain that for the Chebyshev measure, any polynomial, the error range behaves like 1 over r square, is upper bounded in 1 over r square. And this proof we can do for the Chebyshev measure because we had this big tuplets matrix sitting into it, into the moment matrix. For a general Jacobi measure, we don't have this, and it's not clear how to make this proof work, but other techniques will enable us to deal with the general case of Jacobi measures. So we have just seen how to analyze the bounds for the unit interval or the hypercube, because for the hypercube it's just a product of unit interval and it extends very easily. So let me now tell you how we can already use this analysis for the unit interval to understand the case of the sphere. So we are going to make a number of reductions in order to get back to the univariate case. So the first reduction is that actually, it's enough to understand the case of a linear polynomial again. So as we have observed, we had this trick that we could replace f by its quadratic upper estimator obtained using Taylor. But now we are on the sphere, so actually this quadratic term here is actually linear because x and a lie on the sphere. So we have a linear upper estimator. So in other words, it's enough to analyze a linear polynomial f, and up to rotation and translation, it's enough to analyze the case when f is x1, coordinate x1. And we are going to reduce to the analysis of the interval. And we do this as follows. We go back to our univariate problem of minimizing x1 on the interval -1, 1, which we equip with a suitable Jacobi measure. This is our blue measure mu. And we know how the error behaves. This is what we have just learned. And we are going to see how, if we pick univariate optimal sum of square density for the bound corresponding to this polynomial optimization problem on the interval, then we can build a nice sum of square density for the multivariate problem of minimizing x1 on the unit sphere, and where the unit sphere is now equipped with a Haar measure. And this is based on just doing an integration trick, which tells how to integrate a function of x1 on the unit sphere. You can reduce it to integrating the same function x in h of x1 on the interval, but now you pick a different measure on the interval -1, 1. So precisely this measure I'm considering here. And this integration trick, you can do it for h and you can do it for the product x1h. And the point is that the constant c, which is appearing in both equations, is the same. So by the choice of our optimal h, this integral is 1, And here we just now apply what we have learned for the univariate case, and we are able to show that we get an optimal sum of square density, which shows this convergence in 1 over r square for the case of the unit sphere. So the details are not important. What's important is that actually we can build on what we learned for the univariate case in order to understand how the bounds behave for any polynomial optimized over the unit sphere. And actually the analysis is tight. So it's tight for a class of linear polynomials shown here. So there you cannot, for this class, one can show that you cannot do better than 1 over r square. This is really the best one can show. And this is based on a very actually simple link to cubature rules. So, and this link is true not only for the sphere, it's true for any compact set K. And it's saying the following: suppose you have a cubature rule on K, which is exact for integrating polynomials of degree d plus 2r. Then if you take a polynomial of degree d, the bound, corresponding bound of degree r, which is expressed here, well, you now use the cubature rule to do the integration. So you get, you can express the bound like this. And well, now you just replace every f, which is evaluated as at one of the points in the cubature rule. You just replace it by the minimum of f, the cubature points. And what remains here is quantity, which is equal to 1 because h was a density. Its integral was equal to 1. So we see that the bound fr is at least the minimum of f over all the cubature points, which is at least the minimum. So the range, the bound fr minus f min is at least the difference between the minimum of f about the cubature points and the minimum of f. So if we have a set K equipped with a nice cubature rule where we know how the behavior of f is, then we get a lower bound for the error of the bound fr. And this is exactly what's happening for the unit sphere. There are some cubature rules which are known, which are built from the roots of Gegenbauer polynomials, and then we know everything. And this is why we can deduce this, the fact that the bound 1 over r square, the rate 1 over r square is tight. So if we, I promised in the table that we can also analyze other compact sets like the box, the ball, the simplex, round convex bodies. So we will do this by using one more trick in a sense. And this trick, which we call local similarity, which will enable us to lift a result from a set K hat equipped with a weight function W hat to another pair K W. So we suppose here that K hat W hat is a pair where we understand the behavior of the bound. And our goal is to understand the behavior of the bounds for the new red pair. So F is our polynomial, A is the global minimizer, and we have this setting that the set we want to understand, the red set K, is contained in K hat, and we have a weight function on K. W hat is a weight function on K hat. And we suppose that we're in the following setting. So the first assumption is that the two sets K look similar at the minimizer A. So we better look at the picture. So we have K is contained in K hat, and in red is the point A. And the two sets are similar at the red point because there is a small ball around the red point, which has the same intersection with K and with K hat. So in this setting again, the two sets look similar at the red point. So this is the first condition we want. And this is a natural condition because remember that we want to approximate the Dirac delta at the red point. So if we put a Dirac delta at the red point and we look at it on K or on K hat, well, we, roughly speaking, we see the same thing. And the next conditions are talking now about the two weight measures. They should look the same. They should be comparable in the neighborhood of the global minimizer A. So the W should be at least a positive constant times W hat on a small neighborhood of the point A. And the last condition is that W should be upper bounded by W hat. And if these technical conditions hold, then we can claim that F has an upper estimator G on K hat, which is exact at the point A, which means that both have the same global minimizer at A. And the error for the new pair is upper bounded by the error at the old pair, K hat, W hat. So this is the error which we understand. So if we have this assumption just satisfied, then we can also understand the new pair KW. So this is the tool which one can now apply to get information about more sets and more measures. And a small observation is that these two first conditions hold clearly if the global minimizer happens to lie in the interior of the set K. Okay, so now let me just now very briefly mention how we can use this to transport the known convergence rate we know for the interval to some new sets and new measures, some more sets and some more measures. So first of all, what we can do is let's just take the same set, minus 1, 1, but with a new weight function. And this new weight function is of Jacobi type, but now with a larger range of lambdas. We knew only to do lambda is minus a half, but now we can do any lambda at least minus a half by doing this similarity trick. Yeah. The next thing we can do is any set K, any compact set K equipped with a Lebesgue measure. So W is 1 means the Lebesgue measure. And in the case when the minimizer lies in the interior of K, because then you just put your compact set K inside a big box equipped with a Lebesgue measure and you're done. So we only have to worry from now on about the situation when the global minimizer is on the boundary of the set. Next set we can try to understand is the case when K is a simplex equipped to the Lebesgue measure and the minimizer is the boundary. So this is how the simplex would look like. And while there is a simple trick in order to get back to a setting we understand is just do a linear transformation to make your simplex look like this. And then it's nicely sitting within a cube and the cube we understand. So, and the minimizer is on the boundary. So then we will have this local similarity around the global minimizer if the minimizer is on the boundary here or here. Because you can always manage not to put it here, otherwise you turn again your simplex. So we can do the simplex. We can do the ball. And for the ball, actually, it's getting back to the unified case by doing an integration trick. So a bit similar to what we did for the case of the unit sphere. And finally, we can do a class of convex bodies, which we call round or looking like a ball, equipped with the Lebesgue measure, which means, so what do we mean by this? We mean that if you take a boundary point, there is a circumscribed ball tangent, and there is an inscribed tangent ball inside, sitting inside K. Yeah? So really every boundary points you can find a ball tangent inside and a ball outside tangent. So the boundary is very ball-like. Yeah? This can also be characterized in terms of conditions on the boundary, which would be C2 and some strongly convex property. No, yeah, I forgot exactly, but this can be characterized. So we can do a larger, big class of convex bodies, these round convex bodies, but this is not dealing with all convex bodies. So for instance, one simple convex body which cannot be handled with these techniques would be just take the unit ball of the L4 norm. So the norm 4 of X at most 1, so the unit ball. So this is not round. So this cannot be handled. So, but yet we can get information for general convex bodies. And this is what I want now. Oh, so Samir, I think I'm going close to my time limit. So
yes, please go ahead and finish. No problem. You can take some few minutes to finish your talk. No problem.
I think I need 5 to 10 minutes. Is it a problem?
10 minutes. Okay, that's good. Okay, let's go.
Okay. So in order to deal with general convex bodies, so then we have to take the other approach, which is to go back to the idea that we want to approximate the Dirac measure by a sum of square density function. And we do two things. We will go back to this idea, and the second thing we do is to go back to the univariate case. So we have mu is the measure supported by the set K, think of the Lebesgue measure. And we are going, and F is the polynomial we want to minimize. So we are going to consider the push forward measure of mu by F, which we call mu F. So this idea is also an idea of Jean Lasserre. And so this push forward measure is supported by the image of F of K. So just recall here what means the push forward measure. So this motivates defining weaker bounds. Instead of optimizing over a general sum of square, what we can do is take a univariate sum of square S, which we evaluate at f of x. And in this way, you get a bound, let's call it tau r of f. So this is weaker because you are restricting yourself to a much smaller set of sums of squares. But and I here have reformulated the bound in terms of the push forward. So in this way, you get the weaker bounds. But the nice thing is that these weaker bounds still converge to the minimum of f. So this was shown by Jean Lasserre in a recent paper. And the question is, what can we say about the analysis of this bound? Because if we can analyze this bound, the weaker bound, then we can also analyze the stronger bound. And for these weaker bounds, we can show the convergence rate with a logarithmic factor. And so how would you do such a thing? So one thing you could think is that these bounds are reformulated as minimizing t. That's a univariate problem. Now you want to minimize t over f of k. So it's a perfect univariate problem with respect to the measure, this mu f, which is a push forward measure. So by the general theory of orthogonal polynomial, we know that the bound is the smallest root of the orthogonal polynomial PR plus 1 with respect to this push forward measure. But the trouble now is that we have no idea in general how the push forward measure looks like. So we have no control on the orthogonal polynomials and on the smallest root. So we don't know how to use this in order to analyze the bound. So this is why we need another approach. And the other approach is, let's just go back to the start point, which is to try to build a nice sum of square polynomial which approximates well the Dirac delta. So up to an affine transformation, f of k is the interval 0, 1, and you want to find a nice sum of square which approximates the Dirac at 0. So there are lots of polynomials, but let's just look at the green polynomial which is shown here. So this is the needle polynomial which are used in approximation theory by Kroetz-Fetitz. And this is a needle polynomial which we are using, and it's built in terms of S squares of Chebyshev polynomials. So this needle polynomials provides the way to show the convergence analysis and enables us to show this convergence rate in log R over R square. And the natural open question is this log R factor an exponent of the analysis, or is it needed or not? My guess is that it's not needed, but we don't see how to get rid of it. It's okay, so this is my last slide, so I want to conclude. So we have analyzed this general upper bound FR, and I've just now indicated how we could even analyze this weaker univariate variant bounds. And what is the advantage? The bounds are weaker, they have about the same behavior, but, and one could think that they are easier because you can get them as small as eigenvalue of smaller metrics. But computing the entries is way more expensive because you need to integrate powers of F. So this is a drawback. So there are pros and contras. So the analysis for polynomials actually extends to rational functions. And the analysis for the bounds actually do tell us something not only for the polynomial optimization problem, but they also do tell something about the general moment problem. So any error bound for the polynomial optimization problem translates into an error bound for the general moment of problem at the price of losing a square root. But so this analysis for polynomial optimization is applicable to a wider setting than just polynomial optimization. So, and I want to conclude here. Thanks a lot for your attention.